Hi everyone. As promised, here is your YouTube video on the lesson that you all missed. Um, so I want to start by saying that we're going to go over the homework that was due the day you all left for Quest. I wanted to go over the graphs specifically. I think based on our conversations in class, I was pretty confident with where we were when it comes to manipulating the real exponents, right? There's some radicals in there, but I felt pretty good about that. I want to talk about 33 and 35. So if we have y is equal to 3x and y is equal to 3 to the x minus 2. And so when we don't really have any restrictions here, right, in terms of what our inputs should be. So we can just go with our standard -2, -1, 0, 1, and 2. And so 3 to the negative second is going to be 1/9. Then we get 1/3, 1, 3, and 9. All right, so we can go and graph those. And so I'll do 0, 1, 1, 3, and then 2, comma 9. And then, like I said, right, -1 is 1/3, and -2 is 1/9. And we kind of just have to do our best there to estimate. And so when we look at the graph, it's pretty clear, right, that as x goes to positive infinity, our y values are going to go off to positive infinity. And like I said, right, we could graph all those fractions too, but in our last class, we learned about the horizontal asymptote, right? So we put our little dash line here, and we know that when we raise 3 to a power, it's never actually going to hit 0, right? The range is 0 to infinity, where 0 is exclusive, okay? For 3 to the x minus 2, we can do it pretty similarly. And so, except for this time, right, 3 to the negative fourth will be 1 over 81, and then 1 over 27, and then 1/3, and or 1/9, sorry. Let's see, yeah, 1/9, and then 1/3, and then 2 will correspond to 1. And so at this point, we actually don't really have a lot of information, right, in terms of numbers that are greater than 1. So if I plug in 2, it looks like I will be at 1. So let's actually keep going a little bit more. I think I'll do 3 and 4. And so this will be 3 to the first, which is just 3. And this will be 3 squared, which is 9. And so we get 3 comma 3, and then 4 comma 9. And so once again, it looks like as x goes to infinity, our y values will also go off to positive infinity. And again, there's all those decimals or fractions, right? Numbers less than 1. And so it turns out that just like the last graph, right, we'll end up over here. Okay? And so I think the interesting thing to note here is that the graph y equals 3 to the x, right? How does it compare to the graph for y equals 3 to the x minus 2? And this is kind of like the test question where I took a parent function and I made a slight tweak to it. You graphed it, and then I was like, tell me how it shifted from the parent function. And so this one shifts 2 units to the right, right? Everything shifts to, our y values are the same, but they've all been shifted over by 2, right? And so the reason that that happens, right, shifts 2 units to the right. The reason that that happens is because we're changing our exponent, okay? So usually when we see a negative sign, we think, oh, negative means left. But here, actually, we move our graph to the right because we have to add 2 to our x values to get back to where we started. So if we want to have 3 squared, x now has to be 4 because we're going to do 4 minus 2 to get back to 2. All right? And again, that's really the point of our next unit, all about transforming functions. But I just want to give you a little bit of a sneak peek, if you will. And I think the other thing that's interesting here is that our graph only shifted to the right. And so the range is actually still 0 to infinity, where 0 is exclusive. So again, it shifts to the right. It doesn't shift up or down. So I think the takeaway here, right, is that when we change our exponent or our x value, in this case, the range stays the same, right? The range is still 0 to infinity, where 0 is exclusive. Our next one, y equals 2 to the x, right? We're pretty familiar with that one, so I just stuck it on here. The hint on Moodle I said is that you should rearrange the second function. And so we get y equals 2 to the x minus 4 plus 3. And so when we go to plug in our points, I think we should just start with 4, right? We can try to maybe avoid the decimals and come back to them at the end. And so if I plug in 4, right, I get 2 to the 0 plus 3, which is just 1 plus 3, which is 4. And then 5, 6, and 7 spit out 5, 7, and then 11 actually ends up being off the page. So we do 4, comma 4, and then 5, comma 5, and then 6, comma 7. And then, like I said, 7 is going to be off the page. So it looks like, right, our function is going to go something like this. And so I think the question is, well, what's going to happen when we plug in 3, 2, 1, etc.? And so if you look at our original function, right, y equals 2 to the x, our horizontal asymptote is at y equals 0. So if we're going to add 3 to all of our y values, it makes sense that our horizontal asymptote would now be at y is equal to 3. And it turns out that that is true. And we can prove that algebraically. So if I have 2 to the x, right? I already know that 2 to the x is strictly greater than 0, right? That was actually essentially the point of the first one. I know it's 3 to the x, but it's the same idea. Right? We know that 2 to the x is an exponential function, so it's going to be strictly greater than 0. But if we have 2 to the x minus 4, if we just focus on that for right now, right, we saw a number 33 when we change our exponent, we only shift the function left or right. And so we actually know that 2 to the x minus 4 is also strictly greater than 0. And now our goal is to make the current function 2 to the x minus 4 is greater than 0, right, look like the function 2 to the x minus 4 plus 3. So just like we did in our last unit, I can add 3 to both sides. And so I get 2 to the x minus 4 plus 3 is greater than 0. Or it's greater than 3. Good catch. And so I can go and put that horizontal asymptote at y is equal to 3. And so that's what my new function looks like. And the important thing to note here, right, is that we have x minus 4 as our exponent. So we have to add 4 to all of our x values to get back to where we started. So we're going to shift our x values. We'll shift the x value. Well, the point is that we shift 4 units to the right. And then we shift 3 units up. And that's coming from the plus 3, which is going to only affect our y values. And again, this idea of transforming parent functions is where we're going to go in the next unit, but hopefully this will help us out when we get there. I think the key takeaway here, though, is that you can actually calculate the range using our techniques from the last unit, which is pretty cool. And so now, if you want to open your notebook to a new page, you can date it whichever date you fill it out, but we're going to be talking about solving radical and exponential equations. And so here we have k of x is equal to 3 to the x, and then h of x is equal to 2 to the x. And so I think at this point, you don't need the table. So 3 to the 0, of course, is 1. 3 to the first is 3. 3 squared is 9. And then we know that we'll have that horizontal asymptote here. And then for h of x equals 2 to the x, right? 2 to the 0 is 1. 2 to the first is 2. 2 squared is 4. 2 cubed is 8. And so we end up with this. And I think the takeaway here is, or the question, I guess, is which function is going to grow faster? And perhaps it's unsurprising, right, that 3 to the x is going to grow faster. And the reason for that is because you'd much rather triple your money, right, than double it. And again, the reason it'll grow faster is because the base is bigger, right? So you can write that 3 to the x grow essentially as becomes more and more positive as it approaches positive infinity, right? 3 to the x will grow faster than 2 to the x because the base is larger. Now, the next question is, well, do these functions ever equal one another? Again, it would probably make sense the answer would be no, right? That might be your instinct because 3 to the x is going to grow so much faster. But uh, if you look at the graph, they're both going to intersect when x is equal to 0 at y is equal to 1. And so you're going to need that for your homework over the weekend. So keep that in mind. We'll talk about that in our next class. And so now I want to actually dive into solving our radical equations. So here, if we have the square root of x is equal to 4, right? We know at this point we square both sides, and so we get x is equal to 16. And that's pretty straightforward, but we do need to check our work, right? We do need to check our work. And so one thing that I want to change for this unit is that Mr. Riley likes to write left-hand side and right-hand side. In the past, I've been telling you to treat the equal sign like a question mark. But I've seen some of the upperclassmen math, and this is how they do it. So I just want to make sure we're aligned. And so the left-hand side, pretty straightforward, right? Square root of 16 equals 4. And of course, the original right-hand side was also 4. So we're all set. Okay. And again, that seems kind of like obviously Mr. Gallagher. But I want to remind you that a couple units ago, right? Anytime we squared both sides of an equation, we did check our work. And the reason is because 4, right, does not equal -4, but 4 squared does equal -4 squared, right? They're both equal to 16. And so this should set off some alarm bells in your head, or hopefully remind you of a definition we had from before the break. This means that the reason we have to do this is because f of x equal to x squared is not 1-to-1, right? So both 4 and -4, right, when squared go to 16, but 4 does not equal -4. And so the reason when we square both sides of the equation, we have to check is because the parent function x squared is not 1-to-1. And we're going to come back to that definition in a few minutes, so keep that in the back of your head. Our next goal, right, I guess another way to think about this, right, is that we could rewrite the square root of x now as x to the 1/2 is equal to 4. And so we would rather have x be to the first power. So we know what x is, right? Isolate x. And so that's really why we square both sides of the equation. And so when we get into some more interesting equations here, again, I want to have x raised to the first power. So instinctively, you might say, hey, I got to raise it to the 2/3 power, but -3/2 times 2/3 will be -1. So we got to raise it to the -2/3 power. And so now we have x to the first is equal to 8 to the -2/3, which is 1 over 8 to the 2/3. So that'll be the cube root of 8, which is 2, squared is 4. So this is equal to 1/4. And again, we do need to check our work. So the left-hand side is 1/4 raised to the -3/2. I think it's actually easier to flip the 1/4 to be a 4. So we get 4 to the 3/2. So we're going to take the square root of 4, which is 2, and cube it, which is 8. Again, you should probably write that out, but for the interest of time, I figured I'd do that. And then the right-hand side was 8 originally. So we are, in fact, all set. The next one, you might want to pause the video here and quickly solve it. It shouldn't be too bad. And then check your work. Assuming you have now paused the video, I'll progress. Right, so we have the 3/2 power, so we want to raise it to the 2/3. So we get x minus 1 is equal to 8 to the 2/3, which is going to be 4. And so we add 1 to both sides. So we get x is equal to 5. And we'll check our work. And so we get 5 minus 1 to the 3/2, right? That's our left-hand side. And then that will be 4 to the 3/2, which is 2 cubed, which is 8. And then that's where we had on the right-hand side. So we're all set. Now, I, again, would recommend you pause the video here and try this one because it's actually a good conversation starter for a few different reasons. Before you try it, I would note that only y is being raised to the -1/2, not 2y. We had a good conversation about that back in the fall, right, where we had like r times s to the -1, right? People wanted to say that's 1 over rs, but it's r times 1 over s. So that's my word of caution. So pause the video, try it, and then I'll tell you the answer. So again, assuming you've done that. The goal here is to isolate y to the negative 1/2, right? We want to raise y to the negative 1/2 to the negative 2, so that we just have y to the first power. But before we can do that, we need to isolate y to the negative 1/2. So we're going to divide by 2. So we have y to the negative 1/2 is equal to negative 5. And now I get to do what I wanted. So I get y is equal to the negative 5 to the negative second. So I can rewrite this as 1 over negative 5 squared, which will be 1 over 25. And so seems like the answer is 1 over 25. But if you checked your work, and hopefully you did, you'll find that it doesn't work. So if we look here, 2 times 1 over 25 to the negative 1/2. This is 2 times 25 to the 1/2, which is just the square root of 25, which is 5. So we'll get back 10. But the right-hand side was negative 10. So this actually does not work. And so what we can say is that we have no solutions. We can say that we have no solutions, right? This is actually an extraneous solution, right? It's a solution to it's a solution to this equation here, right? But it's not a solution to our original equation. And so we actually have no solutions. And you could, again, so this is why you have to check your work. However, you could have figured this out earlier. So if we go back to this step, right? We have y equals negative 1/2, y to the negative 1/2 equals negative 5. And so instead of thinking about this in exponential form, we could put it in radical form. So this is 1 over the square root of y equals negative 5. And this should set off some alarm bells in your head, right? Think back to our u sub unit. Think back to what we just talked about with the range, right? This is never true because the square root of y is always greater than or equal to 0. Or you could say that 1 over the square root of y will be strictly greater than 0. Okay? So when we do this in u sub, we didn't have the vocabulary right to talk about the range. But we did have quite a few equations that looked like this. So I just want to point out the relationship between the exponential form and the radical form, and how sometimes the radical form can actually save you a little bit of work. But again, either one is fine. The takeaway is check your work when you do these types of problems. Now I want to switch into solving exponential equations. So we have 8 to the x equals 1/4. And if you look back at your notes from right before you left, our big idea was common bases. And so 4 and 8 are both powers of 2. So 2 is going to be our common base. So we can rewrite 8 as 2 cubed. And we can rewrite 1/4 as, for right now, 1 over 2 squared. And then this becomes 2 to the 3x. And we want to make sure that we have a 2 to a power on one side and 2 to a power on the other side. So now we get 2 to the negative 2. And so you really probably want to equate the exponents, right? 3x equals negative 2. We can solve for x really quickly. And you can equate the exponents. But I want to talk about why we can do that, because it's important. And it's something we've talked about. So the way I wrote this in class the other day, and I liked it, I said basically what we're asking ourselves is, if 2 to the 3x equals 2 to the negative 2, right? Well, then 2 to the 3, then 3x equals negative 2, right? That's the statement that we want. And so that actually should sound pretty familiar, okay? But if it doesn't, let's think about it this way. Let's let f of x equal 2 to the x. And so now we can think about 2 to the 3x is just f of 3x, right? I've plugged in 3x as my input into the function 2 to the x. And so I'll write this as f of 3x is equal to f of negative 2. And so now our statement says, if f of 3x equals f of negative 2, then 3x equals negative 2. And that is just the definition algebraically of what it means to be 1-to-1. And so we can say this because if you go back to the graphs from the beginning, right, we know that the function 2 to the x, the black one in this case, is 1-to-1. And you should ask yourself why we know that. And graphically, we know that because it will pass the horizontal line test. Okay, so kind of cool. So the takeaway here is that we can do this because our exponential functions are 1-to-1, right? we can say this. We can say this because f of x equals 2 to the x, right, is 1 to 1 by the horizontal line test. Right, and in this case, we do have the graph, so we can use it. And so if we go back to where we were before, right, and we keep going, I should write an H there. We have, let's see, so we have 2 to the 3x is equal to 2 to the negative 2, and now we can equate the exponents. And what I want you to write is because 2 to the x is 1 to 1. All right, the takeaway is that we can't do this by magic, right? It doesn't just like happen to work out. The reason is because 2 to the x is 1 to 1. And in speaking with Mr. Riley, I think last year he had his guys do this for the first time, and so I'm going to do it this year too. I think it's something you guys can handle. But just a quick explanation, right? You don't need to write me the paragraph. That was me explaining why it works to you. But I do want that quick little because the exponential function, in this case 2 to the x, is 1 to 1, and then x is equal to negative 2/3. And so we are done with that question. All right. If we keep going here, this one I think you could actually pause and try to figure out. The common base is going to be 7, and you can rewrite the square root of 7 as 7 to a power. So try that and pause the video. And now I'm going to assume that you did that. And we're going to rewrite 49, of course, is 7 squared. Raise that to the x to the minus 2. This is going to be 7 times 7 to the 1/2. And so, again, power to a power, we multiply them. And so we're really going to distribute 2 into the x minus 2. So we get 2x minus 4. And this is 7 to the 3/2. And we know that 7 to the x is 1 to 1. So I can, in fact, equate the exponents. I suppose we don't know what the graph of 7 to the x looks like, but it's going to look pretty similar to the graphs of 2 to the x and 3 to the x that we've already seen. And so again, we can do this because 7 to the x is 1 to 1. And so we have this equation. It's pretty simple to solve, but I'd recommend that you multiply by 2 on both sides to clear your denominator, where we had an entire unit on that. So 4x equals 11, and x equals 11/4. And now, now we have got this question. We've got this question, and I would ask that you think about what this looks like. And hopefully it looks like a trinomial, just with a 3 to the 2x and a 3 to the x instead of like an x squared or an x. And so this should remind you of u sub. So if we let u equal 3 to the x, right? That's what we want it to be. We should just check our work. So I can rewrite 3 to the 2x as 3 to the x squared. And then this is 6 times 3 to the x plus 9 equals 0. And so this is u squared plus 6u plus 9 equals 0. And so we get u plus 3 squared equals 0. And so u will equal negative 3. And so, of course, right, we're not done. 3 to the x equals negative 3. But this should, again, set off alarm bells in your head, right? We know that the range of 3 to the x is strictly greater than 0. So this is never going to be true, right? This will never be true. And that's because 3 to the x is strictly greater than 0, right? That's the range. So again, you put the x through it. I do want you to justify, right? Because 3 to the x is greater than 0. And we can conclude that we have no solutions. Okay. So again, we did that with u sub, with the square root of x, right, is equal to a negative number. Same idea. And now I would ask that you pause the video and try this one. It's a pretty similar idea. I think you can figure that one out. And again, assuming you've paused the video, I'm going to let u equal 3 to the x. So u squared plus 4u minus 5 is equal to 0. So I get u plus 5, u minus 1 equals 0. Again, two numbers that multiply to 5 and add to negative 1. So u is equal to the negative 5, or u is equal to 1. And so I'll now say that 3 to the x is equal to negative 5, or 3 to the x equals 1. That's never going to be true, right? Because 3 to the x is strictly greater than 0. And this one, we can rewrite 1 as 3 to the 0th power. And so x must equal 0. And again, we can do that because 3 to the x is 1, 2, 1. Okay. Again, hopefully you caught the solution for you that doesn't work. And then the last question, uh, this is typically like a challenge homework question. So I think I've talked a little bit too long at this point. But my hint to you is that we probably would like to make u equal to 2 to the 1/3 x, right? That's probably what we want to make u. But the problem is we have this, our power over here is not just 2 to the 2/3 x, it's 2 to the 2/3 x plus 1. And so before we can do anything, we need to rewrite this as 2 to the 2/3 x. And we know that if we multiply common bases, we add the exponents. Here, we're adding the exponents, which means we can rewrite and essentially work in reverse. And we can think about this as 2 to the 2/3 x times 2 to the 1st, right? And then bring everything else over. And so again, usually we would work from this step to this step, right? We multiply common bases, we add the exponents. Here, we're just undoing that. And now you can let u equal 2 to the 1/3 x. So you get 2u squared minus 3u minus 20 is equal to 0. And I would recommend that you finish this one on your own. Note that you can factor this. You have to get two numbers that multiply to 2 times -20, which is -40, and add to -3. And I will tell you that the answer is, I believe it's 6. So I'll leave that to you. X ends up being equal to 6. And if you want to talk about it more at my desk in the MRC, I'm happy to chat. So again, I know I went on a little long, but thank you guys for watching. Good luck on the homework, and I'm excited to see you back in class early next week. Thanks. Bye.